Also, a lot of times this Wheatstone bridge trick is utilized in the problems to find the net resistance or the net capacitance also in certain circuits. So let's say this is what your Wheatstone bridge networks looks like. Sometimes it's not directly given like this. It's sometimes given like this, some R1, and then you have R2, a resistor here, something like this. Like you'll have to identify that a lot of circuits don't actually look like Wheatstone bridge, but they're actually Wheatstone bridge when you actually convert them, right? So the condition here is if your R1 into R4 is equals to R2 into R3. If this happens, then the Wheatstone bridge is said to be balanced. In that case, this point and this point will have to be at the same potential, B and D. Your VB and VD, they have to be at the same potential. So that means this element can be removed. This element can be removed. A very, very important point, because sometimes what's given is you have these capacitances, you have something like a C1, a C2, a C3 and a C4, right? Something like this is given to you, and they'll randomly put another capacitance C5 in the middle, and then they'll ask you what is the net capacitance between the points A and B, right? How do you do that? Well, it gets very, very complicated. You have to assume charges on all capacitors, then solve KVLs to get the net capacitance. But if you identify that your C1, C3 is equals to C2, C4, if that happens, then your Wheatstone bridge is said to be balanced, right? Just like your R1, R4 is equal to R2, R3, your C1, C3 is equal to C1, C4. That means your opposite products are the same. Then you can say that the Wheatstone bridge is balanced, and in that case, this point and this point will be at the same potential, so this element in the middle can be ignored. And then you can see the problem has become very simple. C1, C2 is in series, so the capacitance between A and B now is C1, C4 in series, which is C1, C4 divided by C1 plus C4, right? And then you have C2, C3 in series, so you have C2, C3 divided by C2 plus C3, and these two in parallel, so you just add them up to get the net capacitance. Likewise here, one more important point, if you have a Wheatstone bridge which is balanced, then you can replace these two elements. That means you can put the element here, you can put E here, and the balancing condition will remain the same. That means what I'm trying to say is your R1, R2, you have R3 here, R4, you can put them like this, you can put your cell here, and you can put the element here. Let's say that the element is E, right? Even here the balancing condition will remain the same. If you interchange the cell and the element, the balancing condition does not change, it remains the same. So remember, try to identify Wheatstone bridge networks in your circuit. At least one question in the paper should have a Wheatstone bridge which you have to identify, and then use this particular trick to simplify your problem.